Okay, so this was one way, but it sounded very, it was very heuristic, right? Like why 2 colors, why 4x4, like sure, like we could have tried many different things. And the main thing which it was trying to really do, like the reason it was able to get any compression was because it was exploiting the spatial correlation in the data, right? But we know better ways on how to handle with the correlation in the data, right? We have actually spent some time looking into it, which can help us decorrelate this data and then allow us to use a simpler and standard techniques of scalar quantization. And the idea is transform coding, right? Okay, so this is the block diagram for the transform coding, but now for images. Again, we have seen this time and again in the past 2 lectures. You start with some original image. You start with some original image. You convert it into transform coefficients. You quantize and do other things like lossless compressor, use an entropy coder. That gives you quantized transform coefficients, and then you inverse transform it to reconstruct the block. The only addition now is, so far we were working with 1D transforms, right? A transform was just a vector. But now for images, we can think of this as 2D. Let's work with grayscale image for now, for a second. So now you have 2D images, right? So what you have to do is, okay, first variable is your block size. So you figure out like, okay, what's the B by B size block on which I'm going to run my transform. So that's equivalent to, for example, that parameter 2, which we looked at in the last class. That gives you one of the original image block, and then you do some transform on it. And then when you inverse transform on it, you again get a 2-dimensional block. So the only sort of new addition is now your transforms are acting on 2-dimensional signal instead of 1-dimensional signals. And then you can use it to reconstruct the original image. Okay, everyone comfortable? Okay. So just to recall, a transform was like we were thinking of only linear transforms so far, right? We have restricted ourselves to thinking about linear invertible transforms. So in this case, what has changed is now your A is actually the same as the transform. But now your input X is a matrix. Earlier it used to be a vector. So now it's an image block of size n cross n. But you can also arrange it as a column vector, right? So no one is stopping you. You can figure out how to linearize this. And now your transform matrix is something which is then n square by n square, right? If you have n by n block, that basically means you have n square dimensional vector. And so your transform matrix is now n square by n square, and that gives you again n by n transformed components. And when you do inverse, you just inverse it. And again, we are looking at orthonormal transforms, so you don't actually have to run the inverse. You can just take the transpose, and that's much more efficient. Computing inverse is like n cube if you have n by n matrix. Cool. So that's basically the only addition to what we have seen so far in class. And again, just a reminder, like, so this is an image we saw in the notebook during the last class. So let's just recall what our 1D DCT vectors actually looked like. So in this case, our example was with block size n, and our DCT matrix was just n square, where the example I showed you was with block size 8. And so this is what your DCT transform matrix looked like. And we briefly mentioned, like, if you look at the first row, which will give you the first transform component, that's basically the DC value. That's basically the average value of whatever input pixel blocks you are giving it. Sometimes this average value, and you will hear this term DC component in a lot of multimedia compressors, basically refers to the average value. The origin of this DC is like direct current, if you have done electrical engineering at some point. But it's a very commonly used term. So if you see like DC component, don't get confused. It's just people saying like average value. Okay. And then you have for the other bits of transform values, you have these higher frequency components, right? So that's what DCT was doing. As you were going higher and higher here, you were accounting for higher and higher frequency components, right? And again, sorry, I didn't write it here, but these are referred to as AC components sometime. So everything above except DC, like the first component, which is the average, is sometimes referred to as AC components, again, referring to alternating current. So you have some frequency behavior in this thing. Okay, so this was the case for 1D DCT vectors. Now, I'm curious how the 2D DCT vectors would look like. Again, sorry, I should have highlighted. Another thing to notice here, right, was as you move down, your signal was higher and higher frequency, right? So you can see this had more yellow values in the first half than second, then this seemed like there is some split here, more higher and higher frequency components, right? And this is how your now DCT transform matrix looks like for the 2D DCT transform. So first thing is your block size now is n by n square. So your DCT matrix is n square times n square, which we just saw. So here it's again an example with 8 by 8. So this is like your first transform, and you have basically an 8 by 8 matrix. And each of them is individually 8 by 8. I don't know if it's visible, is it? But you got the idea. Okay. So this is your DCT transform is now going to be n square matrices, each of n square size. Okay. And one way to think about these 2D DCT is like it's exact generalization of 1D DCT, where we were taking these quantized cosine values, but now for a 2D cosine transform, 2D cosine wave. And one very nice thing about 2D DCT is that it's separable. So you can basically get 2D DCT transform by just doing a 1D DCT transform along one of the dimension, and then again 1D DCT transform along the other dimension. Okay. We'll see this idea in more detail, so don't worry about it, but this is really one of the very nice properties about 2D DCT, that it's a separable transform. Okay. So let's try to interpret this this set of matrices like 2D DCT. Let's try to understand what it's really doing. Okay. Any thoughts? Like, do you see some patterns here for these 8 by 8 matrix blocks? Again, not a trick question. Like, I'm sure there are, yeah, some patterns there. You can just shout it out.
The first row of matrices kind of has the same pattern as we saw for 1D, where we have like just flat for the first matrix, and the next one is like it goes from low to high, and then an increasing frequency after that.
Yeah. Okay. Exactly. So Sean answered that. Okay. First row of this series of matrices seems very familiar. It's like it has similar vibes to the DCT 1D matrix, where the first one seems just like a white, like just containing DC components, and as you move towards right, it seems like, okay, you have vertical bars which have sort of higher and higher frequency as you're moving towards the right. So, okay, great observation. Any other observation?
The column is the same way.
Exactly. So obviously now if you look at just the first column, you see similar pattern, but now instead of vertical stripes, you have horizontal stripes, right? What do you think is happening as you are moving towards the, what will it be for you guys? Bottom right.
It seems like a product of like the first row and the first column.
So if you look at like just the first column, it seems like your frequency is increasing in the horizontal stripes. If you look just at the first row, it seems your frequency is increasing for the vertical stripes. And if you kind of go look down along the diagonal, it seems like you have sort of mixed, right? Your frequency is increasing along both X and Y directions, so as to say. So like But if you look maybe to this guy here, it seems it has more frequency along the vertical dimension than along the horizontal dimension, which sort of matches the same guy at the top. And so essentially what this 2D DCT transform is doing, as what we would intuitively think, is it's capturing frequency in horizontal and vertical directions. Right? So again, if this hand wavy treatment, it's still hand wavy, but okay, if this literal hand wavy treatment wasn't good. So, okay, the first component here, the first matrix, is just the average value again. So this is like the DC component. So you just see it's pure white. It's just giving you the average value of that block. As you move towards the right, your horizontal frequencies are increasing, right? So if your vertical stripes are increasing in higher, are coming up in higher and higher frequency, that's to say like the x-axis frequency is increasing. Similarly, if you're along the column, as your horizontal stripes are increasing in frequency, that's to say the vertical frequencies are increasing. And as you go towards the, again, sorry, what is this? Bottom right, you're basically mixing, right? And depending on where you are in the array, you can think about whether it has more higher frequency component along the x or higher frequency component along the y. Cool? Everybody comfortable with the idea? Okay, so let's look at a few examples. So this, on the left, I'm going to show some image blocks. These are, I think, 24. This is actually 24 by 32, but it's okay. It's not really, I don't really need to make it square. And on the right, I'm going to show the 2D DCT transform, basically, of these things. So for the constant image, and yellow is high, blue is low. So dark blue is 0, more yellow, higher the value of that DCT component. So for a constant image, you just see a blip at DC value, everything else is 0. For this image where you now see some frequency along the x, and it's a very specific one, you see again a delta function, so as to say only one component. Here is 1, everything else is 0, which is what we expected. Now if you have some other patterns of images, again like, so these are like exact DCT component basis, so these are like the exact DCT component matrices. You again see like blips. So this whole image, if you were converting it into some transform, like if you were converting it into transform components using 2D DCT, you actually get an extremely sparse signal, right? You basically get only one non-zero value. So again, going back to our compressor hat, wearing a compressor hat, that's very good. Like I can throw away all the different components and just keep that. And then instead of compressing these 64 components, I could just compress one. So this is how like the same idea of decorrelation and energy compaction at play. Let's look at maybe some more realistic examples. So this is actually a very popular image. I'm not sure what's the source of this image, but I've seen it a lot in classical image processing classes and all. Let's try to look at the DCT components for 3 different blocks. So again, this is this. This checkerboard pattern is here, and then these are just like those small blocks from this image. And let's try to look at the DCT pattern for this. And so for this first image, so this is like just this particular region in the image. What I see is now my DCT spectrum looks like this. So again, you see like most of the values are 0. But now you don't really have, in practice, you won't really have just a single component with non-zero value, right? You'll have multiple of them. And so this is what you see, but again, your DCT is extremely sparse. And why do you expect that? So let's again recall why DCT was a good transform, right? It's because your natural signals don't really have a lot of high frequency component, right? And so this is what you are seeing in this, for example, this particular image or this particular example, that your natural images are really smoothly varying. You don't really have any higher frequency component. So this is like another block from that image. And again, you see your DCT is DCT is sparse. But now you see the colors are more spread out along the x-axis, and y-axis is basically all 0. And do you expect that? Like, does it make sense? Okay. I see quite a few nodding heads. It does, right? Because if you look at this image, it seems it has some stripes which are going in the horizontal direction, and DCT is picking that up, basically. But still the signal is sparse. And now if you look at that checkerboard kind of thing where there was this tablecloth kind of plug, now you see much more higher frequency components. There is like a lot more action happening. But I would say, interestingly, it's still very sparse. You would have expected this signal, like it has a lot of high frequency component, to be like involving a lot of stuff, but no. And that's because our basis vectors, which are composed of this higher DCT, have these higher frequency components, right? So this image can be represented by linear combination of just these guys and weights. Finally, if you had like a noisy image, right? So this is an image which you probably don't expect to see in nature, right? It's basically just noise. If you have a really noisy image, then, oh, sorry, this shouldn't say sparse. DCT is not sparse. Right? Now if you have noise, then you see a lot of these different checkerboards. Okay. People comfortable with 2D DCT? So let's look at an example. So now we talked about 2D DCT. So you know what I'm gonna do next. I'm gonna truncate using this 2D DCT. That's what we did last time also with 1D DCT, right? That's how we will exploit it for compressor. And so this is just a puppy. And you can see, like, when you just keep the 0 DCT component, so basically just the 0 at DC component, this is your reconstruction, which is expected. At that point, you're just basically storing the average value of pixel in that block. As I increase my DCT components, so basically what I'm doing is I'm zeroing out all the values in those components which are above this. So this is my threshold. So if I keep just like the first few DCT values, this is my reconstruction. And already you see it has gotten the structure of the dog already, right? And this is just with 2 DCT components in this case. So we zeroed out 62 DCT components and still could recover this. Maybe I can add more, right? So at around taking first 8 DCT components, now my reconstruction looks really nice, right? And so this is the power of essentially transform coding, right? You could transform which decorrelated and did your energy compaction, and that allowed you to really throw away a lot of frequency components. And there will be a question on homework for you guys to play with these things for image compressor, tying together transform coding, so it will be fun, but basic idea is basically, you saw what the basic idea of the transform coding is. And so I'm not going to repeat this, but I think we have seen, now I've repeated this many times, for natural images, your DCT is sparse, your energy is concentrated in the lower frequencies. This basically gives you this energy compaction, which you can exploit to do smarter compression. And this is really one of the key observation of JPEG compression compared to like color quantization or other things which we saw before. Okay? Yeah. Everyone with me? Any questions? Cool. So let's look at the JPEG compressor now. How your JPEG compressor works is you first have your image, you do some color treatment, and then you have this JPEG encoder, which consists of forward DCT, quantization, and lossless encoder, which finally gives you the JPEG. Like, is this part familiar? We actually talked about it in last class, right? Like, this is like the basic block of a lot of, I would say, bare bones practical lossy compressor consists of these 3 steps, right? You do some transform coding, you do some quantization, you do some entropy coding on top of it. So again, I want to highlight that a lot of design decisions for JPEG are based on the ideas of how human vision properties work, and we'll have a dedicated lecture on it. So today's lecture will not cover a lot of these things. So take it with a pinch of salt. It's not really JPEG. It's like, say, a simplified JPEG at best. Okay. So the first step during JPEG compression is this color transform and subsampling. And let's see why do we need to do this. So if you look at the RGB components of an image, even the RGB components are extremely correlated, right? Like they have this same spatial correlation. And why do you want to store them independently? So you would like to somehow exploit this. And one way to exploit this is you convert this RGB, it's called color space, to something called, for now, Y-CRCB, color space, which basically decorrelates this color component. The main idea really is you can use one channel to actually store the average values, which basically captures the structure. And then you can use the other two channels. These are also called like chroma channels. So your Y is also called luma channel sometimes. And your CRCB are called chroma channels. Chroma just means color, right? So you can decorrelate your image from RGB to one channel just storing the average value. So in this case, you can see like this mountain structure is translated mostly to the grayscale, in some sense, image of this RGB channel. And then the chroma components take into account the color, which together will determine, okay, how this is supposed to look like. Again, luma channel is just the average value for now. Let's think. It's not exactly the average value, but for today's lecture, let's assume it's the average value. So this is the idea of color transform. Makes sense why you would like to do that. It immediately improves like the correlation across the colors, like it decorrelates them. And then the second part is called chroma subsampling. And this now combines the fact of the subsampling idea which we saw at the beginning of the class, which is, let's say this is your image in RGB space. You first convert it into YUV. So this, you can see it's like the grayscale sort of version of this image. These two contain some color ideas. So all of these are single channel. And then you selectively downsample just the chroma channels. Okay. And the main idea really is that, oh, my luma channel already contains most of the structure. I can tackle more loss in the colors, right? I'm more sensitive to if you change the structure compared to if you change the color that much. Recall like when we were doing color quantization and transform, I could actually get away with like reducing a lot of color information without introducing a lot of new distortion. And we're going to talk about like what this 420 means in the human lecture, because a lot of these ideas are also derived from how human vision works, really, like why you could do this. But this is essentially the idea of chroma subsampling. So first step is you convert it into YUV, and then you do more subsampling for UV than Y. You can differentiably do that. And this is really like this is an example of how this works out in practice in terms of number, why this is again a very simple but powerful idea. So this is an image at 429 KB. And when you JPEG compress this image without any downsampling, so all these four images are roughly equal quality. So you can see they look roughly same distortion. When I just do JPEG compression without any downsampling, I get 323 KB. Okay. But when I do this chroma downsampling, first of all, I get some advantage by just downsampling. So that's what we expect. That was the first idea we started with. If you downsample, you'll get some compression. And if you look at these two images, they look very similar. So even when you like downsample the chroma part, it's not really visible in this case. But even more advantages comes after that when you apply JPEG, like a bare bones lossless compressor on top of this chroma subsampled image. Now you could get an image which looks very similar but takes only 176 kilobytes. Remember, without downsampling, it was taking 323. Now it's like almost half. So what I want to say is like you're not only gaining benefit by throwing away the samples, you're actually gaining a lot of benefit because now once you throw away the samples, your images are much more correlated, right? If you have a much bigger array, pixel array, that introduces more details, that will have more high frequency component. But if you already downsample it, that's like low pass filtering. you have introduced much more correlation in the data which your compressor downstream can exploit. So it's like a win really in two different ways. One, you throw away the data. Second, oh, my compressor can now compress better while basically maintaining very similar quality. So it's like really powerful. You have already gone from 429 to something like 176 kilobyte without really doing much. And so the first step really is like this color start, like, so I'm just now adding some details, like, so that when somebody comes and talks to you about these things, you can understand that. So we said RGB to YCBCR. Sometimes you might hear terms like Y-CBCR, YUV, Y-UV. All of these are equivalent for now. But if you want to learn more about this, you can come talk to me. All of this has to do with a lot of historical context and how color spaces work, things like that. And the core reason for this, why this whole thing works fine, is there isn't really much, especially like this chroma downsampling part. It's actually our first exposure to a very concrete design decision which was taken based on how human vision works. And we were able to do this because our human vision isn't really as sensitive to colors compared to the Luma component. So we already started exploiting that, hey, MSE is not the only thing which matters. Actually, at the end, this is going to be consumed by humans. And we'll learn about these reasons in the next class. Okay, so let's continue then. So we talked about the color treatment. Let's go look into the details of our more familiar block. Any questions on the color treatment and chroma subsampling? No. Okay, so let's continue. So now we'll just basically look into each of these blocks. You already know, so I'll just fill in some more details for you guys on how exactly this works in JPEG. Okay, so step one, we want to do 2D block DCT, right? So you want to convert your image into blocks. So in JPEG, you basically take 8x8 block sizes. So let's say this is your image. You cut it into 8x8 blocks, and then you subtract 128 from it. That's just to center the pixel. So 8 bits is 256 unique values. When you subtract 128, that just centers all the pixels. And so this, for example, is this for instance is an example of one input 8x8 blocks, and this can have like different values. So 220. So let's work with grayscale image at this point because we have already done color treatment and everything before. So now we can imagine we just have one channel, right? So once you look at maybe this particular block in this image, it looks something like this. And what is this grayscale image? It's at the end of the day some uint 8 integers, right? So you have some values 221 to all the way 94. So 94 is dark. 221 or 230 are like brighter values. Okay, so you have got, this is your one 8x8 block. And then the second step is like after you have converted your input 8x8 block and zero centered it, you run the 2D DCT, which we talked about. And that will again give you an 8x8 transformed block, right? And the way you do it is what I was saying earlier, that one good thing about 2D DCT is that it's separable. So you can basically apply 1D DCT along the x-axis and 1D DCT along the y-axis, and that will give you the 2D DCT. And we saw that even when we looked at that 8x8 matrix blocks, like it seemed like it was completely separable around the 2 dimensions. So the way you work around this is once you have this input 8x8 block, you first do DCT, 1D DCT along the rows. So I'll just do DCT along the first row, I'll do the DCT along the second row, so on and so forth. And that will give me this 1D DCT along X. And then I'll take this input of 1D DCT along X. And next thing I'll do is I'll just do DCT across columns. So I'll do DCT across the first column, 1D DCT across the first column, second column, so on and so forth. And that eventually gives me, both these steps combined, gives me this 2D DCT. Yeah.
Right, I got a little lost before. Is your 8x8 block 8 pixels by 8 pixels, or is it chopping the whole image up into 8x8?
So it is 8x8 pixels, so your image might be larger, right? So this is your image. You chop it up into various 8x8 pixels blocks, and then now you are working with one block. You are looking at one 8x8 block. And so these are like the pixel values within that one 8x8 block. Yeah. This is really important. This shows up in image compression everywhere. Okay. And so now, and then you like zero centered it and you did this 2D DCT transform. So at this step, we have the transform components, right? So this is just showing like you started with this single block and you'll get some values, and now your 2D DCT transform might have positive or negative values. This is when you're implementing all of these things becomes important, because now you have to take care of the sign also in your actual implementation. Okay. So that's all I have to say about the 2D DCT transform part for the JPEG. So things to remember is it's very efficient, separable, right? What that means is your complexity is, instead of 64 by 64, right? Because it was n square times n square, that was the metric. So instead of 64 by 64, you can now get away with 2 8x8 transforms. So you have drastically reduced the number of operations which you have to do just because this transform was separable, right? So this is just, I saw one confused face at least. So this is n, our block size was n, and so that's 8x8. And so this was n square times n square, and this is just 2 times n square, because 1D DCT takes cost is n square, whereas 2D DCT the cost is n square times n square, right? So that's a huge savings just because it was 2D. Okay, so continuing, after you have done the 2D transform, you want to do some sort of quantization. That's really how you trade off between rate and distortion. This step is also called like rate controller in some compressors. So just throwing out a name, but again, you can, like if you hear rate controller somewhere, don't get lost like what happened. That's just basically saying how you trade off the rate with distortion. How this works out in JPEG is you actually have these fixed quantization tables. And all you do is like, you're basically doing uniform quantization, right? Like scalar quantization of each channel. So the way you can do it is you just divide by these numbers and you store the integer value of those numbers. So for each element, so here I have 338, I'll divide it by 16, I'll store the integer value. Similarly, here I have minus 10, I'll divide it by 99. And that's basically going to lead to 0 because I don't have really any remainder. Okay, and you basically can take off the sign, so you will see the quantized DCT. You can keep the sign aside and just take the number and divide it. And so basically, if you have a higher quantization table value, and these quantization table values have been predetermined. Again, if you have to guess like how they have been predetermined, that's a lot of fine tuning on like human experiments and what works for us. But it still has a very obvious pattern, which is if you look at the elements towards the bottom right, they are much higher than elements towards the top left. And that's expected because you want to more strongly quantize the higher frequency components compared to the lower frequency components. Again, recall all your water filling, all the different ideas which we have looked at. Right? So this is how JPEG really is comparing the rate distortion. And so you basically have different quantization table for different compression rate. It's not really a fixed. Once you fix this quantization table, your rate is sort of fixed, right? So you have basically these different quantization tables for different quantization rate. And again, like the values of these tables are designed based on like this water filling idea and human vision properties. Again, like I think one of the questions in the next homework will make you go through these things yourself, so you'll appreciate this idea a bit better. And then the final step is really the lossless encoding, right? We finally got these quantized integer values, but now this is a discrete signal. I can losslessly compress it because now you see there are like lots of, for example, zeros in there, so I should be able to compress it better. And for this step, JPEG uses a modified Huffman encoding. And so it's quite complicated. Yeah, it changes quite a lot, but the main idea really is like what JPEG does is it does run length encoding followed by Huffman table. So if you're not aware of the run length encoding idea, The idea really is, so first of all, you go in a zigzag fashion. And the reason you go in a zigzag fashion in images is just because they are more correlated when you go in a zigzag fashion than if you were just going along X and then you go up. These two pixels are really far away, so they are less correlated. So you go in this zigzag format, and then you just look at the symbols. Okay, so first I have 90, then 90, okay, this is done. Then it's followed by minus 40. Then I see a 0, right? And then I see 2 more zeros, then I see 5. So I see this, and so on and so forth. But this I can actually write it as 90 minus 40, and then I can say, oh, I had 3 zeros. And then I had 5, and so on and so forth. I don't really need to care for 0 as this. So this is like the vanilla run length encoding idea. So run length encoding. And in JPEG, actually, you go one step further. So this is like a variable length encoder. In JPEG, you actually go one step further, and you actually store these triplets. So you see like 90 showing up, but then it has 2 more, like a tuple before it. And what this tuple is really saying is that, so 90, so the third number is just the value. So 90 minus 45, like the non-zero values. The first number is the number of zeros preceding that value. So there was no 0 preceding 90, so my first number is 0 here. No 0 preceding minus 40, I have 0 here. Oh, before 5 I have, oh sorry, the second tuple. No wait, yeah. Did I do something? Oh yeah, sorry. I actually did wrong run length encoding here. You don't really go in this zigzag manner. You actually go in sort of, you go in this zigzag manner. Okay, so I think I made a mistake by just going in this zigzag manner, the zigzag manner I showed, but that was just to give you the idea of run length encoding. So here in our example, there is only 1 0 preceding 5. So you have that. And then the second number actually is the length of the integer in bits. So the second number here, it's basically number of bits in unary encoding of 90. So that's just saying log 2 of whatever your third number in the triplet is, right? And so the idea of doing this really is that if you were to, so recall the Huffman code, go back to the question, homework 1, right? If you were to just use a vanilla Huffman code for this thing, quite a lot of different values. You can have 0 to 255 unique values, and your Huffman code actually can have a very high depth, depending on the probabilities and how you are merging these symbols, right? It can be extremely unbalanced, and you don't really know what that tree looks like beforehand, right? So recall, like one way to get over that is, since this is a variable length code, another way to do Huffman encoding on variable length code is I can store the length separately, which is just the number of bits which I need to read, for example, for 90. And then I can run the Huffman encoding on just this length. And Shubham also covered it briefly in gzip in a slightly different setting, but that's basically the idea. So that reduces the Huffman table encoding complexity by quite a lot. Yeah. And then we are not going to go into this, but there are even more concepts around entropy coding, which is like, oh, it's quite complicated. You need to take care of the signs. You actually do different paths for DC versus AC. So in the sense, you have different Huffman encoding tables for the DC component compared to the AC components. And the reason really is like you basically have much more smoother variation in the average component than the AC. And then we also know that the average values are more important to preserve, right? Like similar going back to the luma and chroma. Like how you combine across blocks, it's actually also different for DC and AC. For DC, you actually combine across blocks. For AC, you don't combine across blocks. So there are lots of like coding up an actual JPEG end to end it's no joke. Like people spend a lot of time and did this, but we can still appreciate all the main ideas here, right? And so this is like really the summary for JPEG compression, which is The first step was color conversion. So your RGB is converted to YUV. Your color channel is such that like each color channel is encoded independently of each other, like we do YUV independent. And then we went on to do our bare bones lossy compressor. So you did like block coding where JPEG encodes each 8x8 block independently. And again, this is except the DC coefficient. So be careful, like DC coefficient you do encode across block, but otherwise you do independent encoding of blocks. And then finally JPEG uses Huffman, but in practice you also have support for arithmetic coding, but it's hardly used. Okay. And so like this is our original image which we started with, like 40x uncompressed. And this is the same image with 80x compressed using JPEG. And in this image again, now you can see like all these artifacts, right, which we pointed out. And now you can actually explain some of these artifacts. If you see, a lot of these artifacts looks really like square shaped, right? Why are they square shaped? Because now we are doing things independently in each 8x8 block. So like each 8x8 block is processed independently, and you can have these discontinuities which are quite obvious to the viewer, right? Go look at it at home. So this is just like a JPEG decoder specification. We looked at the encoder, but the decoder actually needs to read these bits. And so there are like lots of, again, star marks on, oh, you have to tell it how many heights and widths of the pixels which are coming in. You have to encode the Huffman tables. Remember again, the homework 1 problem, you either need to communicate the Huffman tables or you need to give enough information so that the Huffman tables can be built. So a lot of stuff is like around like how the Huffman tables is built. You have to store your quantization tables. And then here is your image data in this whole thing. But this is just like a bitstream specification of what the JPEG looks like. Cool. Any questions? So at this point, we understand JPEG. We understand a very basic traditional lossy compressor. But there are obvious ideas on how it can be improved, right? Like it had, it was very good at the time it was designed. People had lots of computational limitations, and it actually performs great, but you can improve it. And so BPG kind of improves it by doing two main things. One, in JPEG we had 8x8 blocks, right? But BPG basically allows for larger blocks as well as variable size blocks. So you don't really stick to 8x8. Sometimes maybe the image has more correlation in a bigger block size compared to the smaller block size, right? And you can exploit all that. For example, that checkerboard pattern, you won't have much correlation in 8x8, but if you have, I don't know, a very smooth signal, you can maybe increase your block size and get even more benefits in terms of decorrelation, right? Because higher the block size, it will push more things into the lower frequency component. And the second thing it exploits really is that blocks are not independent. So that was another very basic limitations. And both of these limitations carry over straight away from transform coding basics and quantization basics we have talked about, right? Bigger block size, variable length block size, you can do different things. Your blocks are not independent. You can maybe use them to predict. You can use predictive coding, so as to say to even compress better. And so we don't have to go into details, but this is what the image compression for JPEG again looks at the 137x, where it was horrendous. And if you do it by BPG, where you allow for all these variable length blocks, predictive coding, as well as, what was the third thing? How larger block sizes, then you can get this image at 8 KB. Now you can clearly see these two are at same sizes, but basically what I want to highlight is there is like a lot of space to improve compared to like just the JPEG in terms of quality. And yeah, so I just wanted to show you guys one thing. Not this. Interesting, yeah. So this is just some example of this bunny image. And this is for BPG. You can now see that there are different length block sizes, right? Like, so when you found a huge constant region, you could increase your block size. Where there was more changing stuff, you could reduce your block size, so that better exploits like the rate distortion. You can better exploit the water filling. And the second idea was of predictive coding, where if you think about these two, blocks, they are exactly the same. They are almost the same. So maybe I could just store, the previous block, and that has already done most of my job, even in terms of transform coefficients. So I have to save even less pixels. Just to highlight how BPG exploits these things. Again, based on this very simple example. And cool, so what's next? So in next class, we'll go over some learned image compressor. So after the Thanksgiving break, so you have Thanksgiving time. Homework 4 won't contain any other content from the future lectures. So it will contain content up to today's lecture. In the next 3 classes, we are gonna go into a bit more advanced concepts. And so come with the mindset of really enjoying and learning and seeing what we can do better. So the first idea really is we have been really artificially been stuck with the idea of linear transforms. Maybe we can go beyond linear transforms to improve our compressors even further. So far, we haven't even given it a thought in the transform coding world. And the second, in JPEG, you saw that there were a lot of these hand designed parameters, I'll go to YUV, I'll downsample UV by 2, I have these fixed quantization metrics. Think about it, that fixed quantization matrix, it's hand designed for each particular rate. So each of those 64 values, somebody decided I'm going to put a 13 there, right? Which doesn't seem like we should be able to do something better. And so the class after the Thanksgiving, we're gonna go over learned image compressor, which essentially extends the idea of image compressor based on these 2 ideas. Thank you.